Hi, my name is Hasbi. I'm a postdoc working mainly in seismology at CAUS. So on this occasion, I would like to present our result on the Zabargad fracture zone in the northern Red Sea. So I will mainly present about the results from the ocean bottom seismometers deployment. I would like to acknowledge my collaborators, Laura Parisi, Eduardo Cano, Margarita Fittipaldi, Guillaume Babi, Nico Agustin, Martin Mai, and Sigurin Jonsson from Kausen, uh, Nico Agustin previously in Guiomar. So you see this satellite image on the right. This is the study area, and you can already see this deep valley in the Red Sea. It's quite clear in the south and to the central, but then it's quite this is disappearing in the north. So we are going to discuss more about this, and just to show some example, this is the record of the one earthquake that we recorded from this seismometer. So before we dive into the details of the study area, I'd like to probably give a big overview of the Arabia and Africa plate boundary system. So the Arabia is diverging from Nubian plate or Africa along the Red Sea. And so further to the south, they have a connection to the East African Reef, and to the north is the East African Reef, which is the continental reef, and in the north is the Dead Sea transform faults with this transform plate boundary. So I would say could be one of the key regions to study rifting, oceanic spreading, and transform faults evolution. And then we go to the Red Sea. So Red Sea is we could say one of the youngest ocean basin. So roughly 14 million years old or less. And it can be categorized as ultra slow spreading ridge. So if the rates changes from 16 millimeter per year in the south to 10 millimeter per year in the north. One of the main question is the people are still discussing or debating is the extent of the oceanic spreading. So there are one end member that arguing that these are mainly oceanic spreading, and there are also like the other extreme is the mainly continental, uh, but there are also somewhere in between. There are some parts are oceanic and some part are continental reef. Because the major challenge is this Red Sea has a thick sedimentary layer, so mainly evaporates, which cover the oceanic crust and the spreading ridges and faults. So if you see the figures on the right, so the pink area is where actually the oceanic crust is exposed. So this is where area we have mentioned before, where there's a clear deep valley in the middle of the Red Sea. This is where, and so it's from what we call South Red Sea to the Central Red Sea. And to the north is not super clear because there are some area that where oceanic crust are exposed, but then many of them are actually covered by this evaporites. And a more recent study is more keen toward this is already like mainly oceanic reef, but this just not exposed because of these thick sediments. So we zoom in into this area, what we call the Zabargad fracture zone. This is the study area. So Zabargad fracture zone, so we call this the largest offset in the Red Sea. So it's roughly about 100 kilometers. So if you see the figures on the right, so this relatively like yellowish line are where we know there is this ridge axis in the south, and also in the north where there is evidence that there is oceanic crust are exposed. So this is where we know this is the ridge, but we don't really know what happened in between. I mean, there are different models that are proposed to like there are different ridges, so one of several transform faults. So this is still an open question. So how the offset is accommodated. And for seismological perspective, the seismicity are monitored by are all land stations. So the station are located quite far, and then we don't really good have a good earthquake location quality. So, for example, in the figures here, this is from the geological survey of Saudi. So this we see these two scatter seismicity in one in the north and one in the south, where without really clear lineaments or directions. And in terms of seismicity, there was a report about historical earthquakes in magnitude 6 or larger. This is quite important to study the seismicity and the fault infrastructure in this area, uh, well, especially for the coastal cities and the communities. So this is one thing that quite important to invest to we need to investigate. So to overcome this issue, so we under this we call it Zafran project. So this is a project to investigate the structure and the seismicity in the Zabargad fracture zone. So it's not only for seismology, but we also have a work on bathymetry. But I will focus most on the seismology. So this is the first we call the first ocean bottom seismometers deployment in the Red Sea. So the station was deployed for about 1 year from the end of 2021 to the end of 2022. So it consists of 12% bottom seismometers that was provided by the German instrument pool for amphibian seismology, DPAS, that hosted by Albert Wegener Institute. And we also have additional two OBS provided by Fugro. And then additionally, we use six lens stations that are we install, and also two additional stations from the Saudi Geological Survey. And the distribution of the station are shown on the right here. So the pink are the OBS, the pink and the green are the OBSs, and then the blue and the black are the land stations. So we have like what we call it continuous seismic data that are recorded for roughly 1 year, and we want to look at earthquakes. So we need to do earthquake detection. So to identify the earthquakes and also the process the P and SRI faults. So we tested different deep learning algorithms. Uh, but there's the challenge is the we have a very thick sediments, so the signals is quite complicated, and also have a higher noise level compared to probably the OBS in the Atlantic, where the water column is much deeper. But then we tested the different algorithm, and then we do some manual checks. So we finally found about 3,000 earthquakes, which the largest one is magnitude 2.6. So this is one example of the earthquake that we process. And the next step is that we do 1D seismic velocity inversion. So the purpose is to improve the earthquake location accuracy. We use what call it starting model from the ambient noise study from our colleague Eduardo Cano, who did his PhD here, and which reveals so we did this starting model. We generate random model to test several feasible inputs then we pick the best results based on the what we call travel time residuals. So this is what we've already shown. That what's quite interesting is that we reveal this low velocity layer that's related to this what's called sedimentary layers. The next thing after we got the velocity models, we want to improve the earthquake location. So we want to sharpen more the location to hopefully to resolve the fault structure. Or we process what we call hypocenter location. So we use double different locations. This is a relative location. We make use of the similarity of the different of close by earthquakes to tag the location together. The last thing is we analyze the focal mechanisms to determine the faulting type and the orientation. Because the earthquakes are relatively small, so the largest one magnitude 2.6, we use the force motion polarities. So for P, and then we also constrain it with the P and S amplitude ratio to get with more constrained results. And so this is the results. So we identified two distinct seismicity clusters in the Zabargad fracture zones. So we found there's two distinct areas. First is in the north, and then another one in the south. And a plot with the star are the earthquakes with the focal mechanisms. And then I overlay with this relative large scale models that are inferred by different data sets. So the pink one are the risk axis, and then they also put the different models of transform faults, but this is we need to see or test from our data sets for our results. So we zoom in first into the north. So we try to interpret these lineaments of the seismicity, which reveal this is northwest southeast normal faultings in the cluster, and then the seismicity on some parts are actually deep. Like for example, the faults that I mark as F1 and F2, the seismicity goes deeper than 10 kilometers. So it could be the influence of fluids, but we need to investigate it further. One of the key area here is where the oceanic crust is exposed. We call it Mabahis Deep. So there is this part Mabahis Deep, and so the north is underwater volcano. It's called Mabahis Mons. So we have results from high resolution bathymetry in this area. So this I was just to highlight this direction of the faults that are interpreted are consistent with the northwest southeast interpretation from our seismicity, as shown in the rose diagram on the right. And then finally we want to infer where's the location of the ridge axis. So we are quite certain the ridge axis are located in the Mabahis Deep and Mabahis Mons, and we think this part is actually one segment of the ridge, but of course the location is still infer. We probably need further data to actually constrain the actual location. And so we have the first segment here, and then the second one we interpret a second segment. So it's located to actually a brine pool that have some evidence of inactive hydrothermal activity. So they're close to what's called a Cabrit Deep. We put another segment here. And so we don't see any clear evidence of transform faulting between this first segment and the second segment. So this could be non-transfer offset, or the seismicity is not active during this monitoring period. And then we move further south. So this is the second segment. And then south of the second segment, we don't see much of seismicity. So they're relatively quiet. And then we see again seismicity that's also extend quite deep, deeper than 10 kilometers. And we have dominated by normal faulting. So we propose this could be the third segment, but from the surface, from the bathymetry, it is not clear is there any feature that support this segment. And the last one is actually we found the south. We have a different mechanism. So this struck slip faulting with some normal component, and so the seismicity is quite diffuse. So we this in this during this period we see intense of seismic swarm activities. So this could be what causing the seismicity is quite diffuse, and so we interpret this direction of the faults is this direction because this is already what expected from the model that the direction of the transform faults. And another one, another supporting probably data that we look at different publication, for example, lineaments for that was from site sonar that was published by Mitchell and Augustine 2017. They also see this lineaments around this area where this where this location. This is coincide with the fault F4. And so our college now is also preparing the publication for this bathymetry analysis for southern ZFZ that's actually support this interpretation. Uh, so to actually sum up this analysis, so this is the like the bigger view of the in our interpretation of the Zabargad vector zones faulting. So we have three segments of ridge. So S1 in the north and S2 close to the Cabri Deep and S3, and that it's connect to transform faults. Possibly transform fault. This is could be also relatively young because it's relatively short and also have a different some normal components. And then well, also interesting to see is there are some areas that have a relatively low seismicity. This also evident from for long-term catalog from Southern Geological Survey. There is these two area where we also see the seismicity are relatively shallow. This could be related to this variation of the temperature. We know this is this Mabahismon, the volcano. This could be increasing temperature. And in this between S1, sorry, S2 and 3, we are still need to be investigated more. Well, what's the cause of the area of low seismicity? So to sum up, the key findings are we derive a 1D velocity model that already showed this low velocity layers, so indicated thick layers of sediments, and our college is currently already submitted work on the more detailed ambient noise tomography on this area using this data. And then we found two major seismic clusters in the north. So it's dominated by northwest southeast normal faulting lineament driven by extensional process. And the south cluster, so there was the mainly dominated by northeast southwest structive lineament indicating a transform fault segments, and the nearby northwest southeast faulting. And the area, we also found areas of low seismicity will be indicated by possibly related elevated lithospheric temperature. If you are interested, you can scan the QR code and we have a list of the publication for this related to this project. Thank you.